Sometimes when we are computing joint probabilities, such as the probability of A intersection B, we've described this probability as being computed by the product rule. It's a multiplication of the two probabilities. This, however, is under independence, meaning that the fact that B occurs does not influence the likelihood of A, and the fact that A occurs does not influence the likelihood of B. So rather than to write it as the product in this way, it's better to write the product rule as the probability of A times the probability of B given what we know about event A. Now, all this notation means is that we have to look at what is the probability of B after that the event A has occurred. And in some case, like if you're talking about, event A is that you roll a die and you get a 6, versus event B is the event that you toss a coin and get a head. In those cases, the fact that I roll turned out to be a 6 does not at all in any way, shape, or form influence the outcome of a coin toss. So if the probability of B doesn't change given A, then in that case, it's fine to just write the probability of B. But this notation is kind of a more safe version. It's a safety net because here we are saying take into consideration event A. Now also, this could be written as the probability of B times the probability of A given that event B occurred. And these are really identical. It's just still the product of the two probabilities, but the second probability takes into account the first event that occurred. So let's take a look at an example to illustrate this and build on what's called Bayes' theorem. Suppose a company audits emails coming into its server. It classifies each email as either spam or not spam. 20% of emails coming in are spam. So let's just imagine that we have all of these emails that are coming in, all of these emails, and we are going to put them in one of two piles. We're going to either put them in the spam pile or not spam. Now, I'm not going to label, define these sets, but this is the set of all emails that are spam. And we know that we'll label that edge, or that branch, with 0.2 because 20% of emails will end up up here. And similarly, 80% of emails will end up down here. So what we were given is that the probability that an email is spam is 0.2. So the probability that it's not spam, therefore, would be 1 minus that, which is 0.8. Okay, so still, we've accounted, notice, for 100% of all of the emails incoming. Now, this is where we need to make the distinction. Of those that are spam, 70% advertise a product. Okay, so of these, if we were to say, all right, let's break up the spam emails into those that advertise a product and those that do not advertise a product. So I am going to just use the letter A to say advertise a product, and then I will use not A to indicate that they don't advertise a product. We don't know what they are, we just know that they don't advertise a product. So 70% of the spam emails advertise a product, which means that the other 30% of the spam do not advertise a product. They might, be just junk or phishing or whatever types of other things that occur. Now, here's where things get interesting because the probability of an email advertising something is dependent on whether or not it is spam. If it is spam, then that probability of A is 70%. So what does that mean? Well, that means that the probability that it advertises a product given that we know it is spam. Okay, if we know that it is spam, the probability that it advertises a product is 70%. However, of those that are not spam, 10% advertise a product. So of those that aren't spam, only 10% advertise a product. So the probability that it's an advertisement out of all the non-spam emails, only 10% of those are advertising product. Maybe they're from a partner company or sister company or something else. And that means that of those that aren't spam, the other 90% of those do not advertise a product. So notice that we accounted for all 100% here of the spam emails and all 100% of the non-spam emails. And so once again, what we could compute is the probability of spam of percentage of all the emails that are both spam and advertise something, which would be the product of the probabilities, giving us 0.14. The probability or the percentage of emails that are both spam and don't advertise anything would be 0.2 of 0.3, which would be the other 0.16. I'm sorry, 0.06. So that's still got to add up to 20% of emails, 0.06. Notice those still add up to the 20%. And now here we'll have the percentage of emails that aren't spam and advertise something would be 0.8 of 0.1, which would be 0.08. And then 90% of those would be non-spam and non-advertising, which would be the other 0.72. Okay, and so notice once again that we've classified all of our emails as one of these four categories. Now, our question is, given an email is advertising a product, so that's what we know. We've just picked up an email, and we know that it is advertising a product, right? Now, if I didn't tell you anything about that email other than it's advertising a product, how certain could you be that that email was spam, right? So you don't know that it's spam. I'm just telling you, hey, I've got an email here. It is advertising a product. Can you tell me how likely you think that it is advertising spam? So the other way to rephrase this, given an email is advertising a product, what we really mean by that is what percentage of emails that are advertising a product are actually spam? Okay, well let's look at that. What emails here are advertising a product? Well, it's this one right here. That's advertising a product. Those emails right there, those 14% of all the 100% are advertising a product, as are these. These are also advertising a product. So what we're asking for is out of all the emails that are advertising a product, so given that it's advertising, what percentage of them are spam? Now, when you look at this, you might say, well, wait a minute, don't we already know that? Isn't it 0.7? We've got to be careful about that because this 70% says that if you took all of the spam, put them in a bucket, and drew one out of all the spam emails, there would be a 70% chance that you would draw one of the emails that has an advertisement on it. However, this one's a little bit different. It's saying if you took all of the emails that are advertising something and dropped them in a bucket and drew one out at random, what's the probability that it would be a spam email? So notice here the population is spam emails that we're drawing from. Here the population is advertising emails that we're drawing from. So the denominator is totally different. All right, well, let's ask ourselves, first of all, what are all the emails think about this as 100 emails. Of the 100 emails, how many of them are advertising? Okay, well, that would be our denominator, right? Out of all the ones that are advertising. Well, it's the 0.14 plus the 0.08. Those are all of the advertising emails. So out of the 100, you could say that 22 emails are advertisements. And out of those 22 emails that are advertisements, how many are spam? Well, it's this 0.14, right? The numerator has to be a subset of the denominator. And so now you can calculate this, and we get about, let's see, 0.14 divided by 0.22, or 14 out of 22, would be about 64%. So 64% of advertising emails are spam. So, in other words, a majority, or slightly more than 50%, a majority in that sense of advertising emails are spam, and that means that only 36% of advertisement emails are not spam, and that would be the other 0.08. Okay, so notice that what we've done here is we were given conditional probabilities, but the condition was different than the condition that we wanted. We wanted to not look at all of the spam emails because that's not what we know about this email that we're looking at here. We're saying if I know an email is an advertising email, then what percentage of them are spam? Whereas this one says, if I know an email is a spam email, how likely is it that it has an ad in it? Right? Different questions altogether, but it's a very subtle seeming difference. Now, this is a lot of times what we want to do in probability is we want to come up with the conditional. This one is known as the posterior. We'll define this in a moment. Based upon the evidence that we have, as well as a likelihood and what we call a prior. So let's see how we constructed this. How did we switch, find a probability where the condition and the event are actually switched? Well, let's write it this way. It's the probability of S given A. Okay, the 0.14, what is that? Well, that's the probability of both spam and advertisement. Divided by the 0.14. The 0.14 is the probability that an email is both spam and advertising something, plus the probability that it's not spam and advertising. So in other words, these are all the emails that are advertising something, regardless of whether or not they are spam. Now this can even further be deconstructed because the probability of S and A, how did we get that? Well, we took the probability of S times the probability that it's an advertising email given that it is spam, that's the 0.7, divided by, again, this is the same thing, so the probability it's spam times the probability it's advertising given that it's spam, plus, how do we get this? Well, it was the probability that it's not spam, probability that it's not spam, let me try that again, times the probability that it's advertising given that it is not spam. So we have that deconstructed quite well down to the probabilities that we are actually handed. And this is really Bayes' theorem here. Okay, so Bayes' theorem, given two events A and B, if we want to compute the probability of B given A, so that's what we call the posterior, then that's the probability of the percentage of emails that are both spam and advertising divided by all the ones that are advertising. And then now to get the joint probability, because we had a condition, we still do the product rule, but it's the probability of B times the probability of A given B. Probability of B is called the prior. Probability of A given B is called the likelihood. And probability of A in the denominator is called the evidence. And then we just unpack how we get the probability of A from all the bits and pieces. And now we have the full-on Bayes theorem. So very useful theorem in practice. We can answer a lot of important questions about data by using this, where we care to get a posterior from a known likelihood.